So we've talked about pretty much every other arithmetic operation involving matrices except division. So let's talk about that now. First, let's look at scalar. I'll say b divided by a. And I'll start out and say, we'll assume a is not equal to 0, so I can make that division. I can view it as multiplying b by the inverse of a, 1 over a, where our a inverse equals 1 over a for scalars. And I end up with this result for scalars. A inverse A equals A inverse, that equals 1. What we want is a similar thing for matrices. We would like this to be true, where A is a matrix now. If we multiply A by its inverse, whatever that is, we haven't talked about it yet, on the left, it equals the same thing as multiplying it by the inverse on the right, and the result is kind of the equivalent of 1 for the scalar case. It's the identity matrix for a matrix. We'd like this to be true. And we're going to kind of define it that way. For one thing, if you look at this, if A is m by n, you know that I is square, right? Then A inverse would have to be n by m for this product to be square. But then if I multiplied on the right, I would get an m by m. I would get two different things here and here. So a non-square matrix cannot have an inverse defined this way, because we're going to require that you got to do the multiplication from both sides to get the same result. It's a two-sided inverse. So for a square matrix, so now the way we define an inverse, it can only be for a square matrix, and we're going to define it this way. If this square matrix of the same size B exists such that this is true, then we'll say B is the inverse of A, and we'll denote it as A inverse. The inverse might not exist. If it does not exist, we call A singular. That's like dividing by 0. If the inverse of A does exist, you call it non-singular. Those are some just definitions. I don't know if I'll go through this proof in detail, but suppose you've got a B such as this is true and another matrix C such as this is true, but they both kind of satisfy the requirements for being an inverse. If you go through what that means, it means B equals C. B equals C and C equals B, which means the inverse is unique. Whether I multiply on the left or the right doesn't matter. If I, let's see, while I get into this, you could have a one-sided inverse that would work on non-square matrices. But the left inverse would not be the same as the right inverse, and it would not be unique. But for a square matrix, if it has an inverse at all, the left inverse is the same as the right inverse, and it is unique. Here's an example I won't go through, but this is just verifying that B is the inverse of A. Do this multiplication, multiply A times B on the right, and you get the identity. Multiply A times B on the left, you get the same identity, same size, same identity. That means B equals the inverse of A. Here's some other features. Just to get through this quickly enough, I'm not going to go through line by line these little proofs. If you really are interested in the proofs, freeze this chart and just look at it for a while. But the inverse of the inverse, you get back the original matrix. The inverse of a product is the product of the individual inverses in reverse order. This just kind of verifies that that is so. The inverse of a transpose is the transpose of the inverse. You can go through these line by lines and prove them to yourself. The thing we have not done is how do you go about showing or proving or finding that a particular matrix A has an inverse? And secondly, if it does, finding that inverse or computing it. We're going to have to save that for another day and another whole chapter of my textbook. So we are now done with basic matrix definitions and operations. We're not done with all the computations, obviously, but in fact, the next thing we're going to get into is true linear algebra, solving systems of algebraic linear equations.